All right. So I just remember last night that I forgot to assign homework number 5 on Wednesday. So I put one more date on the due date there. So it's online now. The homework 5. So now it's I set the new date to be the 25th, which is Thursday. Okay. Um, and then on the other 2 dates, they are also pushed back by 1 day because of that. So just keep in mind that these dates might be changing depending on the progress we have in lecture. So if we are kind of behind, then we might change those days. Okay, um, as we get close to the due days. But I'll keep you guys posted on that if there's any change. Um, so for the classroom disinfection today, I assigned to Casey and Connor. Okay, um, so we're again looking at chapter 5. So last time we introduced the types of charges, basically two types, charges positive and negative. Um, the like charges, they repel each other, and opposite charge will attract each other. Okay, so that's basically the SI unit for electric charge is coulombs, C. And the fact that material will be charged is because they have different tendency of losing or receiving electrons if they are rubbing against another materials. Okay. Charge is not continuous; it's actually quantified. So that means you have the smallest increment of charge. Okay. So that's 1.6 times 10 to the negative 19 is basically the charge of electron or proton carries. Electron will be negative charge, proton will be positive charges. And a few fundamental numbers that you can look up, they are constants. Mass of electron is a constant, mass of proton and mass of neutron is also a constant. Okay. We talked about the conductors, insulator. So basically, a conductor will have free electrons that can move around through the body, while insulator do not. Okay. You can do charging by contact or charging by induction. All right, so that's having no contact. We talk about the strength of the interaction between two charges. So that's governed by Coulomb's law. The strength is equal to K, or 1 over 4 pi times epsilon, times absolute value of Q1, Q2 over their separation square. The direction of the force is given by a unit vector, which is a line connecting the two charges, depending on if they are like charge or repels or the opposite charges, then you can determine if the force is repulsive or attractive. All right. And if you have more than two charges in space, then the force on any given charge would be summation of the electric force by other forces. So that summation should be vector summation. Okay. And then let's take a look on one more example here on the electric forces. So this one says you have 2-point charges Q1, Q2, 2.0 microcoulomb and 4.0 microcoulomb. They are located at position 1. This is indicated by a position vector R1, 4.0 I minus 2.0 J, and then plus 5.0 K. And then the second one at 8.0 I, 5.0 J, and minus 9.0 K. It's asking you what's the force of Q2 on Q1. Okay. So for this one, you want to probably sketch the problem here to see where the two charges are. All right, so this is three-dimensional problem. We can use X, Y, and Z in that direction. All right, so it's kind of like for R1, it's the minus. So let me see. It's 4 and minus 2 and 5. Or maybe you do this X, Y, and Z here. So this would be X, this would be Y, this would be Z. So wait a second. All right. So minus 4 here, or positive 4 here, minus 2 here, and then Z is 5. So you have to imagine, okay, this is three-dimensional, so probably something like here, over here maybe. That's your R1 vector from the origin to that point. Okay, so this is 4 minus 2 and 5, the coordinates. And then A, 5. So A will be somewhere here, 5 will be probably somewhere there, and minus 9. So minus 9 might be somewhere here. Okay, so just imagine this is three-dimensional. This will be R2 then, somewhere. It's going inward to the board, but so there's a part. Both are positive charges. Okay, so they are positive and positive. So you can see for Q2 on Q1, it should be a repulsive force. So it's going to be in that direction, repulsive going away. So in that direction, okay. So you would need to figure out what's this length, right? This R from 2 to 1, the magnitude of it, okay? So basically, this is what you can do. You can do vector from 2 to 1, that will be equal to, so basically, if you have position vectors, you can do R1 minus R2, okay? That will give you this guy. So some knowledge that you learned from the last semester, you need to use it here. R1 will be 4.0 I minus 2.0 J plus 5.0 K, right? And then I'm going to just put the R2 in the next line here, minus of R2. So 8.0 I plus 5.0 J minus 9.0 K, okay? Then my R from 2 to 1 will be, so 4 minus 8 minus 4 minus 2 minus 5 will be minus 7. 5 minus 9 will be 14. All right, so this is your R 2 to 1. And remember, for the force, in this case, in the vector form, you can write in vector form from 2 to 1, that should be equal to K of Q1, Q2, right? Over R of from 2 to 1 squared times the unit vector of this guy, okay? Now, if you remember for unit vector, you can do it this way. So unit vector of this guy should be equal to the vector itself, right, divided by its magnitude of it. So you need magnitude of this guy here. You need magnitude of it here as well. So we can calculate what's the magnitude first. R221 will be the magnitude of this guy, this vector. So that should be its x squared minus 4 squared plus y squared minus 7 squared plus 14 squared, z squared, okay? That will give you 16.16 in meters, all right? So that's a scalar. The magnitude is a scalar. And then this is what you are looking for, okay? So it's equal to, we can calculate what's this first. The magnitude of that K, Q1, Q2. You should be doing the absolute values, right? Because that's for magnitude there, divided by R21 squared. So that's, you can use 8.99 times 10 to the 9th. Q1, Q2, they are both positive. So you can just take the positive numbers by micro coulombs. Micro means 10 to the minus 6. Okay. Over 16.16 meter squared. So the magnitude of this force, or you can say this is the magnitude of the force without the arrow, that means the magnitude of the force. That's equal to 2.75 times 10 to the minus 4, okay? You can see the units should be newtons because that's for force. You have everything in SI unit. Okay, so that C square will cancel out those two C. The meter square here will cancel out meter square there. Okay, so then you have newtons left there. All right. So then you can write in this way. F21 for the force is a vector is equal to 2.75 times 10 to the minus 4 newtons times the unit vector. Okay, you can do unit vector will be this guy. This is 16.16 meters for the magnitude. And then just put this guy here, 4.0 I minus 7.0 J plus 14.0 K, okay? So this is a vector form, okay? All right. Questions you guys might have on this one? Okay. All right. So I think we have been talking about the electric force or electric field. Yeah, electric force so far, but yeah, electric force for a point charges or point charges. Now, if you have a symmetrically charged distribution, for example, if you have a sphere that has charge distributed uniformly through the body, then for the electric force outside of the sphere, you can treat the sphere as a point charge. Okay, just similar to like when we are calculating gravitational force. we are actually treating that as a point as long as you take the point from the center of the sphere. Okay. All right. So next, we are going to take a look on the electric field. So this is similar to, again, gravitational field. Okay, so when you have two objects um, that are separated by a distance r, then they will have gravitational attraction force between them. Okay, so for two charges, you will have the same. Similarly, while the difference is for gravitational field force, it always has attractive force. Okay, for electric force, you might have attractive, you might have repulsive force. Okay, depending on the size of the charges you have. So similarly, if you have a charge and then the nearby space will have electric field, okay, according to that charge. So this is similar. If you have a mass over here, then there's gravitational field around it. Okay, for gravitational field, it's equal to g, the mass, divided by r squared, depending on where you are away from that center of the mass. Okay, times the r vector. So field is a vector, it has direction, in addition to having magnitude. Okay, so if you have a charge q in space, then the surrounding field will have electric field. The magnitude of the electric field is equal to kq over r squared, similar to gm over r squared. Okay, so that's that guy here. Because the force is equal to kq q0 over r squared, where q0 is a test charge if you have. Okay, so that's typically a small charge compared to the point charge itself, the q itself. All right, so then electric force is equal to q0 times E, just similar to the gravity is equal to m times g, where g is the gravitational field. Okay. All right. So definition of the electric field then will be equal to the force divided by the charge Q0, which has SI unit of newtons over coulombs. Okay, so newtons it's from the force, C is from the charge. All right. Now typically this charge will be smaller compared to the original charge, just like any object nearby the Earth is small compared to the Earth itself. Okay, so then the gravitational field by the Earth is not altered by that mass. Okay, so similarly here. um, so when you are having a charge inside electric field, then F equal to Q times E, F and E, they are both in vector form. Okay, so then you can see depends on Q, the sign of Q. If you have positive charge Q, then field, electric field and electric force, they are in the same direction. If your Q is negative, then your electric field and the electric force, they are in opposite direction. Okay. So like this one, E and F are in the same direction. In this one, E and F are in the opposite direction. Okay. All right. So magnitude by for electric field due to a point charge is equal to this guy, K Q over R square. Okay, we are taking absolute value because for magnitude it should be a absolute a positive number. Okay, and then the direction could be if it's one dimensional, could be positive or negative. If it's two dimensional or three dimensional, then you can specify the direction with a direction vector. Okay, or maybe directional angles. So depends on what sign is the charge. If you have positive charge, then electric field will be pointing away from the charge. Okay. If you have a negative charge, then electric field is pointing towards it, okay? Because electric field is a vector, all right? So then direction-wise, that's how you can tell what sign would be. If you have more than one point source, so say if you have several points charges in space, then electric field at particular point of interest at field point P, it should be coming from summation of the electric field produced by each of the point sources. Okay, now remember electric field, it's a vector, and then you are doing vector addition here again. Okay. All right. So on the electric field, then we are going to take a look on this example here. This one says, yeah, 2-point charges lying on the x-axis. One is 2.4 picocoulomb. So P stands for pico, which means 10 to the negative 12. It's at the origin, and a charge of minus 4.8 picocoulomb is at x equal to minus 10. Now it's asking you to place a third charge at x equal to 20 so that the total electric field at x equal to 10 would be 0. What would be that third charge? So what you can do, you can draw this x-axis. This is 0. This is minus 10, positive 10, and 20. You have Q1 here at the origin, 2.4 PC. You have Q2 here, minus 4.8 PC. You put a Q3 here. So this is positive, this is minus. It's asking you what this would be so that E field at this point is equal to 0. So basically, you can see this is your point of interest, right? So the E field at this point should be summation of E field by this guy at that point, and this guy at that point, and then this guy at that point, okay? So basically, there will be, for Q1, it will produce an E field at this point pointing in that direction. E1 in that direction, because Q1 is positive, right? So the electric field by a positive will be pointing away from it. Q2 is negative. Electric field produced by Q2 at that point will be in this direction. All right. And then you would have a E3. Now E3, because we do not know if it's a positive or negative, so then we do not know which direction E3 is pointing. It could be in this way, right? E3, it could be in this way, depending on E1 and E2, which one. So E1 and E2 are competing with each other. If E1 is greater than E2 magnitude-wise, then your E3 will be in this direction, right? Otherwise, your E3 will be in that direction, right? Because your total has to be 0. So then we kind of have to compare the magnitude of E1 and E2 first, okay? So we can see that E1, for E1 is positive X, so you can write in this way. E1 is equal to Remember, that's equal to KQ, right? Absolute value of Q over R1. And then we already know the direction, that's positive X direction. So positive X direction, okay? Now you can see this is equal to K, E1 is 2.40 PC, right? R1 will be from here to here, so that's 10 centimeter. All right, 10 centimeter. Sorry, I forgot about the squared because it should be K absolute value of Q over square, okay? And that's in the X direction, positive X direction. Now you can write E2, which is similarly K, times absolute value of Q2 over R2 squared, okay? So R2 will be from here to here, which is 20, right? R2 will be 20 centimeter. And right, and then that's in the negative X direction. All right, so you can see this will be K, this will be 4.8 PC over 20 cm square, okay? Minus X direction. K is the same K. You can put the 8.99 times 10 to the 9th for K, okay, if you want. But I don't think I need that because then I just need to compare this number with that number to see which one is greater, right? E1 and E2. This one, E2 4.8 here, that's twice of 2.4, right? So I can basically rewrite that. So that would be equal to K 2 times 2.4 PC, right? Over, at the bottom here, 20 square would be equal to 4 times 10 square, right? Okay, and direction, you can still write it down there. So then this is the same over here, this part, right? It's the same as there. And then this will be 1/2, right? 4 over 2 will be equal to 1/2. So then it looks like your E2 magnitude wise is only 1/2 of E1. So then E1 is greater than E2, okay? So then electric field by 3 should be in this direction. All right, so E3 will be in that direction, not in this direction. All right, E3 is towards the left. So that means Q3 will be positive, right? It should be a positive charge for Q3 because electric field by a positive charge is pointing away from it, okay? For a negative charge is pointing towards it. So then Q3 is positive. Q3 will be positive, okay? So you can tell that your Q3 will be positive. And the magnitude of that, of the E3 should be equal to the difference of E1 and E2, right? So E1 and E2, if just talking about the magnitude, then you can do E1 minus E2 without the arrow. That means just the magnitude. So you can do this guy minus that guy. So it'll be K 2.40 PC over 10 cm square minus the other one, E2, the magnitude of E2 will be 1/2 of that. So 1/2 of K 2.40 PC over 10 centimeter square, right? So then that equals to 1/2 K 2.4 PC over 10 centimeter square, right? That should be equal to your E3, right? E3 should be equal to that. So that tells you E3 equal to that guy And that's K times 1.20 PC over 10.0 cm square, right? Now, for E3, according to the electric field by this point charge Q3, it should be E3 should be also equal to K Q3, right? The absolute value, because Q3 is greater than 0 than it's itself. Divide by R3, okay? R3 will be this guy from here, from 10 to 20, that's 10, right? 10 centimeters square, okay? So then you can tell from here, you can tell that your Q3 will be equal to 1.2 picocoulomb, right? So that's why I didn't need to plug in the K there, because at the end here you can see 10 and 10 will, this is square, not to the third. 10 and 10 squares will cancel out. K and K will cancel out. So then Q3 equal to that guy, okay? So your Q3 is equal to positive of 1.20 picocoulomb, okay? All right. Any questions you guys might have on this one? Okay. So if not, then we are going to take a look on actions of electric field on charges, okay? So if you have charges in the presence of the electric field, so in this case, so electric field is in this direction. Now this charge is a negative charge, okay, minus E. So then that means the force will be in that direction, right? Electric force is in the opposite direction. So then this guy will slow down, okay? The velocity will slow down. It will experience an acceleration of this guy, net force, which means electric force in this time, in this case, divided by the mass of it. Okay, so Q over M times E field. Now, if you have initial velocity perpendicular to the E field, then this guy is going to be deflected, okay, as it goes through the electric field. So if this is negative charge, then it's going to be deflected upward, okay, in that direction. So then you will have oscillation in the vertical direction. You will have no oscillation in the horizontal direction. So then this is similar to like a projectile motion. When you have a horizontal velocity, it's not affected, but vertical velocity is going to be affected, okay? We'll take a look on one example here. So this one says if you have an electron, so electron will be negatively charged by 1.6 times 10 to the negative 19 here. It says initial velocity 2.0 times 10 to the 6 meters per second in the positive x direction. It enters the region that has uniform electric field in the positive y direction. So that means positive is pointing downward for the y direction. E field is 300 newtons per coulomb in strength. It says find the oscillation of the electron. And then how long does it take for the electron to travel 10 centimeter in the x direction? Through what angle and in what direction is the electron deflected while traveling 10 centimeter in the x direction? So you have V0 in the horizontal direction. The electric field should be in this direction, right? Because it's a negative charge, so the electric field is in this direction. F of E, F sub E, electric field. So then it will be deflected in that way, right? It will go in that way. For the directional angle, how much being deflected theta should be equal to tangent inverse of Vy over Vx, okay? All right, I think I can have you guys try this and we can take a look at solution together in a few minutes. Okay. So let's see here together. So when you have an electric field, and then that's on electron, so electric field should be the only force here. If you are considering the gravitational force, actually it's very small compared to the electric field, okay? Because M is only, let me, um, you can take a look on this. So electric field is equal to Q times E, right? So in this case, it's 1.6 times 10 to the negative 19 for the Q. E is 300, right? So that gives you 4.8 times 10 to the minus 16 newtons, right? Now, in case if you are wondering what's the gravitational force, okay, that would be ME times G would be 9.11 times 10 to the negative 31 kilogram times 9.8 meters per second square, right? So how much does that give you? 9.11 times 9.8. That gives you 8.93 times 10 to the negative 30. So you can compare the two, 10 to the minus 30 to 10 to the minus 16, so that you can basically ignore the gravitational force. Okay, so this one is very, very small. All right, so the overall oscillation then will be just coming from the mass of the electron divided by the mass, or the force of the electron divided by the mass of it, electric force. So 4.8 times 10 to the negative 16 divided by 9.11 times 10 to the minus 31. Okay. That would be 5.26, or actually 17 here instead of 16, 17 minus 17, 5.6, 5.269 times 10 to the 13 meters per second square. Okay. Yes. Okay. Um, um, so you were saying in the previous slide, right? Right. So if you do Q over M times E, so that's the same, right? Q is 1.6 times 10 to the negative 19, right? E is 300. Um, so did you get a different number? Okay, so that's the same, yeah. So yeah, so Q times E is the electric force, okay? So the F sub E, the electric force, so the same here. All right. So that's your oscillation. So remember, you want to also specify the direction, right? So this should be in the negative y direction because it tells you x and then y is the downward. So your force is upward, so you want to probably specify that this is in the negative y direction, okay? In that way, so A equals to this guy times negative y. Times negative y with the hat, that means the unit vector y, okay? B is asking you how much time does it take to travel 10 centimeters in the x direction, all right? So then that would be motion in the x direction, and x direction divided by velocity in x direction. Okay, so 10 centimeter means 10 times 10 to the negative 2 meters over the original speed in the that's in the x direction, right? So that's the original, should be the original speed of 2.00 times 10 to the 6 meters per second. Would be 5.00 times 10 to the minus 8 second. Okay, that's how much time it takes. In what angle is that being deflected? So you need to find out what's the velocity after it travels 10 centimeter in the y direction, right? And then you have the original, this is the original velocity in the x direction, because in x direction, there's no force on it. So you have to calculate Vy first. Initially, it's only in the x direction, so that means initial for y direction velocity should be 0. So then it will be just equal to a in y direction, which is that guy, times t, okay? 5.269 times 10 to the 13 meters per second square. Now remember, it's a negative number, okay? So you can include it here. So minus that times t, that will give you 2.635 times 10 to the 6 meters. Negative that, okay? And then for the angle, would be tangent inverse of Vy over Vx. Positive over 2.00 times 10 to the 6 meters per second, okay? It's going to be minus 52.8 degrees for the direction, right? All right. So next, we are going to take a look electric field lines. So we have been indicating electric field with lines. So those lines are actually imaginary lines. They don't exist in the real world, right? Because if you have a point charge over here in the space, you don't see any physical lines. But we use those lines to visualize the electric field. Okay, so we are imagining those lines. So um, so for electric field lines, they are in the same direction of the field vectors at any point. Okay, so if you indicate electric field lines in with the arrow, that means you are indicating the electric field direction also there. They start at positive charges. Okay, so in the scenario of if you have positive charges, then if you have a positive charge in space, then electric field goes in that direction, like radially away from it, towards infinity. Okay, all right, or infinity. So that's the scenario if you have negative charge. Okay, if you have negative charge, electric field lines are pointing towards it. So that means it starts from infinity for a line pointing at that, right? So goes in that direction. So they start from infinity and then points towards the negative charge. Okay. Also, on the third point here, it says they end at negative charge. So that means that like this scenario, they end at there, or end at infinity. So that refers to if you have positive charge in space. So then the field lines are pointing towards infinity. Okay. They are more dense where the field is stronger. Okay, so if you have stronger field, you'll indicate more dense lines. So for example, here in this case, so this is just one Q. All right, so then you have fewer lines than here if you have two Q. All right, now they are opposite charges, so then the lines are pointing differently. Okay. If you have more than one charge in space close to each other, then the electric field line look like this. Okay, so this guy starting from positive charge, ending at negative charge. Okay, so in that fashion. And if you have two Q here, but just one Q here, so you have this less lines surrounding this guy, but more lines surrounding this larger charge. So that indicate larger strength. Okay, if you have two positives same charges, then you'll find that in between you have zero field. Okay, because at the middle here, the field produced by the two charges are exactly the same in strength but opposite in direction. That cancels out. Okay. All right. Also, if you have like more dense field or dense line over here, so that means over here strength field is stronger than the field over here. If you have less dense, okay, so the field line density is there. Okay, a couple more conceptual question here. So on this one says, so electric field lines are indicated here. You have three Qs. You know that in the middle is a negative. So it's asking you what are the signs of Q1 and Q2, Q3, and then find Q1 and Q3 given this negative is 22.8 microcoulomb. So I think we can take a list together here. So field lines starting from Q1. So that indicate Q1 is a positive charge. Okay. Also on Q3, they are starting from Q3. They are lines starting from positive charge, ending at negative charge. So Q3 is also positive. So Q1 and Q3, they are both positives. Okay. And for the magnitude of Q1 and Q3, you can count like how many lines surrounding this known charge here. So they are, if you count them, there are 16 of them here surrounding this guy. There are only 8 surrounding this guy and then 8 on this guy. So then that means Q1 and Q3 are 1/2 of Q2. Okay, because you have half lines, then Q2 on Q1 and Q3. So Q1 and Q3 are half of Q2, so 11.4 then. Okay, so Q1 and Q3 are positive 11.4 microcoulomb. Okay, 1/2 of Q2. The second one here, it says the electric field lines surrounding three charges are shown in the figure. What's the charges? Which of the charges are positively charged and which are negatively charged? Rank the charges in order of increasing magnitude. Okay. Similarly, you can see like Q1 for the sign of Q1, the line starts at Q or QA here, so that indicate QA is a positive charge. Okay. Now QB though, the lines go into QB, so then QB is negative charge. Okay. Q3 or QC here, lines go out of QC, so QC is positive. Okay. So A and C are positive, B is negative. Okay, and then for the magnitude wise, so A has less lines, electric field lines than B, than C. So then magnitude wise, A is less than B, less than C in that order, okay? All right, so we'll stop here for today then, okay? So we're coming back on Monday.